Hello, hello. Okay, is this working? Is it? Okay. Okay, so this is just, okay, hello everyone. Well, it gives me great pleasure to introduce Jasper Michels for the IEE seminar today. Jasper is now originally one of the rising stars, and now he's one of the established top quality researchers. That happens with time. He started his career at the University of Amsterdam, where he got his master's in organic chemistry, no less, and did his PhD in supramolecular chemistry at the University of Twente. And from there, he went to the University of Oxford to work in the group of Professor Anderson. And I remember seeing papers that came out by Jasper in the area of rotaxane, sort of wrapped conjugated polymers that were particularly interesting because they kind of surrounded the octavely active layer with this sort of protective sheath. He did some very interesting work in the photophysics of these materials in collaboration with Professor Richard Friend in Cambridge. That was a very, very nice piece of work that was very well appreciated at the time. He then, from there, returned to the Netherlands to work as a senior scientist in Eindhoven. And 2 years ago, he took up a position as group leader in the Department of Molecular Electronics at the Max Planck Institute for Polymer Research, one of probably the premier places for polymer research right now in the world. And he's going to talk to us today about part of his work, which is broadly centered on the design of conjugated polymers and ways of sort of processing them in order to endow them with a specific property that addresses a technological need. And the title of his talk is Of Devices and Droplets. And not quite sure what that's going to be about, but we'll find out soon enough. Jasper, please.
Thanks, Guy. You did very well.
Thank you.
Okay. Welcome, everybody, to my talk. Yeah, so this title looks a bit quirky, but I hope things will turn out clear for you. But first, let me briefly spend a little bit of words, a couple of words on the institute I work and the department to have a bit of an idea. So the Max Planck Institute for Polymer Research is part of the Max Planck community. It's about 80 institutes around Germany and a little bit outside Germany as well, in any direction basically in science. We have 6 major departments that are listed here. So molecular electronics, that's the department where I'm group leader, headed by Professor Paul Blom. Then we have a spectroscopy department, physics at interfaces. We have a polymer theory department, physical chemistry of polymers. They are focusing a lot on making mini emulsions. And we have synthesis of macromolecules, which is essentially a fairly new department because the former professor, the head of department there, Klaus Mühlen, he retired and the position was taken over by Professor Tanja Weil. So as said, I'm in the group of the Blom department, and we focus on polymer and organic electronics, hybrids. We do, like a lot of people now, also a little bit work on perovskites, transistors, a little bit of bioelectronics or electronics interfacing with biology. We have an independent group. We're hosting an independent Humboldt group that works on organic multiferroics, and yeah, setting up all the facilities that come with that and that facilitating that. So clean room device fabrication. We have got a time-resolved spectroscopy lab. We do a lot of time-resolved and steady-state charge carrier dynamics measurement. That's where Professor Blom is particularly good at. And we also doing nuclear NMR, solid-state NMR. And my contribution to it all is in a little bit in organic synthesis, that we have our little own synthetic effort. Can never be that big. We don't have that much space for it, but at least we need to make our own workhorse polymers and not being too dependent on other groups with that respect. And I'm also doing a lot of morphology studies of active layers in organic electronics, and that's what I'm going to be talking about today. So, and that's also the reason why I called it devices and droplets. So I'm going to talk about blend-based devices, the devices that have an active layer of which the functionality depends on the cooperative action of two materials, like a donor and an acceptor, or a host and a dopant, a ferroelectric and a semiconductor, for instance. You process those in a thin layer, and then phase separation might happen, or it might not occur, depending on what you want and what you need. You have a certain domain size, a certain domain composition. You need to tune that to optimal device functionality. And with droplets, I'm referring to a specific mode of phase separation called liquid-liquid demixing, because we do solution processing here. That's what we talk about. And a lot of things might happen, but one of the things that can happen is that already in the liquid state, before anything crystallizes, phase separation takes place, and you get dispersion of one liquid enhanced in one of your components in the matrix of the other, like water in oil, for instance. But I will be giving more details on that soon. Yeah, so this is the idea. We'll be talking about a ternary blend here. So we have a polymer A, a polymer B, or component A, component B in a solvent that under dilute conditions is stable, but then we cast it onto a substrate and, for instance, spin coat it. The solvent evaporates, and at some point demixing occurs, and the film starts scattering. If it starts scattering, relatively large structures form. Right, so this is a very simple schedule of what could be going on. If we start out with the initial situation where we have solvent component 1, component 2 as a stable homogeneous mixture, then upon solvent evaporations, the components start to feel each other, they interact with each other. This might result in crystallization of one of them or either of them, liquid-solid demixing, or what I will be addressing here is liquid-liquid demixing. So an interface of two fluids, one of them enhanced in component 1 and one of them enhanced in component 2. They can be pure or they can be mixed phases, but with a defined liquid-liquid interface. And because this interface is between two liquids, it's interfacial tension that controls domain size and domain shape. Then if all the solvent is gone, then this is frozen in practically in the dry state. So you're not seeing your actual droplets anymore, you only see their, let's say, imprint in the dry film. Giving a few examples, this is from the field of organic solar cells. This is from a project cooperation with René Janssen in Eindhoven, where they process this PDPP5T polymer with PC70 BM. And if you do that from pure chloroform, you get these droplet-like structures of virtually pure PCBM in a matrix of polymer that contains a little bit of PCBM. And we don't want that, of course, for this particular device, because these structures are too big. So in terms of device performance, that doesn't work very well. And what you can do here is adding a co-solvent, such as dichlorobenzene, I believe they used. And with that, you can essentially stimulate the aggregation of the polymer. So the viscosity rises steeper. That's at least our explanation for this. And you can prevent large-scale demixing. And then at some point, you end up with these much more homogeneous films with much smaller domain sizes, and you reach your highest efficiency. This is another example. That's what we work on in our group at Max Planck. This is a blend of a ferroelectric polymer, PVDF-TRFE, which has these polarized, strongly polarized carbon fluorine bonds. And if we mix that with a semiconductor, a polymeric semiconductor. Here I show P3HT, but the same thing practically we see with polyfluorine-based materials, or FAPT for instance. Then we find droplets of our polymeric semiconductor in a host being the PVD-FT-RFE. And if we've got this structure, we can then modulate the charge injection into the semiconductor by tuning the polarization direction of the ferroelectric. And with that, we can make a bistable, non-volatile memory device. Write our information at high bias and read out at low bias. Here, different than with the solar cell example, we do want these slightly larger structures because it has been calculated that if they become too small, that the local field lines are not in the right direction anymore for charge injection. So here they are, say, desired. They shouldn't go too big, but they should at least be 50 to 100 nanometer for the effect to occur. Then we have my last example that I show here of droplets in these active layers is in the field of OLEDs. Those are very recent results from our group. Here you see a basic OLED structure with here the anode, PLOT PSS, on ITO, and here the cathode barium aluminum, where charges are injected and recombining to give light. In this active layer of light-emitting polymer, we are working on blends at the moment, and we're blending in larger band gap host materials, such as in this case polyvinyl carbazole, also works with polystyrene, and we get phase separation. You see this droplet-like structure. Now, why do we want to mix in these large band gap hosts? Well, we've seen that if you do it properly, then we can alleviate the trap-limited nature of the electron current. And I will consider that as sort of the second part of my talk to show a little bit more on those results. So very interesting, very new. But first I'd like to switch to the actual process of the demixing itself and the role of evaporation on it. Because it's while working on these semiconducting systems, I think we hit some physics that is much more general than just the field of organic electronics. Okay, so these are a small recap. So liquid-liquid demixing, we talk about structure formation in the liquid state. And we're in solution. So that means that the molecules have a fairly high mobility. They diffuse very, very fast. Different than a polymer melt, a blend of two polymers in the melt, right? So there's no solvent. And there the mobility is much lower. Domain size and shape controlled by liquid-liquid interfacial tension. That gives drop-like structures and similar morphologies in the dry film. We're not talking about ordering on the molecular level or the monomeric level here. This is amorphous demixing. Well, there's a very old theory that gives you the conditions thermodynamically where you expect this macrophase separation and where you do not expect it typically. This theory has been given by Flory and Huggins independently around late 40s. It says that the free energy of mixing of a solution, it's a mean field theory, that the free energy of mixing has an entropic contribution, which is negative, which takes the volume fractions of the components, here polymer A, polymer B, and a solvent. It takes molecular size, or relative molecular size, as mapped on a molecular lattice. This is always negative, as these volume fractions are typically smaller than 1. So it's favorable to mix things. You create more disorder. And an entropic contribution here, which contains these Flory-Huggins binary interaction parameters. So they talk about they describe the energetic interaction between the monomers. So if they're positive, the interaction is effectively repulsive. If they're negative, the interaction is effectively attractive. So if you have this equation, let's say from the first derivative we can calculate in the phase diagram of polymer A, polymer B, and the solvent, the so-called binodal line. This is the line that separates the miscibility gap, so the region where the system would want to phase separate thermodynamically, and the stable region where it would like to stay as a single phase. And from the second derivative of this equation with respect to volume fraction, we find the spinodal line, and that tells us in the miscibility gap in which region decomposition or demixing is spontaneous rather than activated. Activated is here in the metastability region. You need to nucleate your droplets before they can grow above a critical nucleus size. Whereas in the spinodal region, they are triggered by the minute density fluctuations that you always have due to temperature. We have good reasons to believe that the structures that I've shown you are all spinodally demixed, because if we do our rough calculations and we calculate these phase diagrams for these materials based on this theory, it is a semi-quantitative approach, but it shows that this miscibility gap in the spinal region is very large. The ratios that we practically use are compatible with evaporation running straight into the instability region, and most importantly, we study them optically, we find a dominant length scale in the morphology. So I'll come back to that, which is very characteristic of spinodal spontaneous demixing. Yeah, so we start in the stability region, solvent evaporates, and you drive the system into the miscibility gap. Now, what does that look like? This is a movie from YouTube by the Tulin group. I think they're in Birmingham, as far as I remember, and they have been looking at this process with a transparent spin coating chuck with a strobe light underneath and a CCD camera. So it means you're always looking at the same spot as it comes by. That starts in the stable region. Evaporation is occurring. You run into the miscibility gap, and you see a structure forming that coarsens. So there's droplets that form and that become bigger. That means they coalesce, interfaces relax, or they grow via Ostwald ripening. Well, we've been looking at this from a theoretical point of view. That's what I want to address here. So we can basically model this with a fairly simple diffusion model. So we can map our concentration fields or volume fraction fields on a numerical grid, and then let the structure evolve based on a free energy minimization. And that enters this generalized diffusion equation via the chemical potential, which has the contribution from, let's say, the mixing thermodynamics, and it has a contribution from interfaces, because you form fluid-fluid interfaces, and that's where the unfavorable interactions still occur. So that's a free energy penalty. Then there are some more ingredients, of course, that we need. We have composition fluctuations as a function of temperature. You need something that sets off the demixing, of course, and that's induced by these density fluctuations. And we have, of course, an evaporation term. One of the components is disappearing. It's a solvent. So that is this here. I'm not going into detail what that looks like, but this is our simple numerical model for that.
The first term is really thermodynamics.
Yeah, so
potential gradient, and then the other two are more the kinetic effects.
yeah, it's a quasi-static approach, indeed. Yeah, indeed. So thermodynamics in there, but it is a kinetic model, absolutely. Right. Well, this is an example of a simple numerical 2D top view simulation, just to show you that it qualitatively works. It gives qualitatively similar structures as we saw in the experiment. The color that becomes lighter is that means that evaporation is going on, and the structures that form are coarsening according to Ostwald ripening and according to coalescence. Okay. Now we've also used this for more complex things. We can include a pattern surface energy and do directed decomposition. We've done that for these ferroelectric memory devices to make sure that the semiconductor goes to the positions that we want to. And we've modeled this and find qualitative agreement between the experimental and the computational morphologies. But for now, I want to stick to the 2D simulation. So that means I assume that there are no concentrations in the vertical direction here. Okay, so now it will become a little bit more technical. I hope you bear with me. I've again drawn the phase diagram here. In this case, it's the phase diagram that we calculated for this PDPP5T PCBM chloroform blend. So based on experimental input. So we measured the Florey-Huggins interaction parameters, or let's say we estimated them based on measurements, based on surface tension measurements. We know our molecular weights, so we have an idea of how the relative molecular sizes are, and we can do our calculation. So you see again the binodal, and in green the spinodal region with a very small single phase region, and I've added this extra feature of these tie lines, and they connect the phases that are at the same chemical potential at which they will phase separate if you are in the miscibility gap. So phase separation going on, for instance, at this position, you get a phase with a lot of solvent, a reasonable amount of polymer, and a very small amount of PCBM, and you get a phase with less solvent and which is virtually pure in PCBM. These arrows is what is the process. So we start here, evaporation goes on, and at some point you get your initial structure. As soon as you hit the binodal, the droplets will grow. But because of the ongoing drift in composition due to evaporation, you will walk along the binodal, so that means that the composition of this phase changes until you reach a point where everything is frozen in. So the viscosity goes up, and at some point no transport occurs anymore. And that's then what you get finally in your dry film. Yeah, so in summary, so between 1 and 2 we have a homogeneous homogeneous mixture. Between 2 and 3 there's the emerging structure, and between 3 and 4 there is the coarsening going on. So the coarsening, the driving force for coarsening is the reduction of interface. The interface is still giving your free energy penalty. And this process is very well known and has been studied for decades. It has been, the theory has been developed, established very well. So with the early work of Kahn and Hilliard, of De Gen, working on it, Kurt Binder, Nigel Clark later. But what we couldn't find is what is now the influence of solvent evaporation on this decomposition, on this spinodal decomposition. So the fact that one solvent, or one component is drawn away from the system. And that's what we've been focusing on theoretically a little bit more. Okay, so to show what the effect is of evaporation, I'm showing two numerical simulations here. One of them here is with the evaporation switched off, and I choose a composition in the unstable region, so at time 0. So essentially you have here a homogeneous mixture. It can't stay homogeneous because it wants to phase separate. It is under this green line. Practically you cannot do this, of course, with a blend of a solvent and 2 polymers, but you can do it with a binary blend of 2 polymers that you quench with temperature in the miscibility gap, and then see how the system evolves. So here you will see the emerging morphology. Then this one will give the DFT, so the discrete Fourier transform. We take a Fourier transform because we want to characterize the system in terms of characteristic length scales. And here you will see the Fourier spectrum, essentially, or the structure factor. So you will see what wave number or wavelength is dominant in terms of in the morphology. And if I run the simulation, you see that the initial density fluctuations develop into an emerging structure, droplets, that subsequently start to coarsen. They become bigger. They coalesce or they Ostwald ripe. And if you look at the structure factor, you see that there is a dominant length scale developing that then decreases with time. So there are 2 regimes. One of them is that the spectrum develops a dominant length scale at a specific Q, a preferred maximally unstable wave number of Fourier mode that is sort of programmed in the DNA of the mixture, more or less. And then the second stage, it starts decreasing because the droplets coarsen. So the length scales get bigger. That means Q is 1 over the 2 pi over the length scale becomes smaller. Okay, so then if I switch on evaporation, we're starting now here, and we're turning the hourglass, or say pressing the stopwatch as soon as we cross the spinodal here, so as soon as we walk into the miscibility gap. So if you look at the situation now here, only with a trained eye you can see that things are a little bit different, but essentially a similar structure evolves. It lightens up a little bit more because of this effect. The domains get a bit more pure, the solvent is going away. But especially I want to focus on the early stages. So here you see that a dominant length scale forms, but it increases first before it starts decreasing. That's what evaporation does to it compared to a non-evaporating system. And that's what we're trying to figure out. Why is that? Why does it first increase and then decrease? So the increase is still happening in the early stage before the coalescence takes place. So that means that the system, let's say, doesn't seem to be able to make up its mind for a while at which dominant length scale it would like to phase separate. But then it does, and you get some emerging structure, and then it decreases again. So this graph summarizes that. So we have, as a function of scaled time, so let's say the point where we get true phase separation, that's what we call 1, tau L, the lag time. We have here, we are already in the miscibility gap. We can discern this spinodal wave number that is increasing in time. And then at the point of bifurcation, it reaches the maximum and it decreases again. And that's exactly the point where you hit the binodal, and this is the phase that becomes more pure here. So the two things to understand for us. One of them is this increase at early stages, and one of them is this is what you get at the end of the first regime. And how does that depend on the physical parameters of the system? Well, to do that, in these sort of unstable situations, what you typically do is a linear stability analysis. You say, okay, at my early stages, I have a mean composition from which you deviate. Those are the fluctuations. But I assume that those fluctuations are still very small, so that the gradients are still very small. And what you can do then is that you can simplify, you can linearize your diffusion equation into something that is analytically solvable. And that is telling you, if you have an analytical theory, it tells you a little bit more how your physical parameters hang together than if you only have a numerical model. So we have our composition as a function of position, as a function of time, equals a mean composition plus a small deviation from the mean. That we stick into our generalized diffusion equation. This is constant, so everything drops out. So you get your change of your composition change as a function of time with a composition independent diffusivity now, and here our linearized chemical potential. Now at this stage it is very practical to take a Fourier transform of that, and we get rid of these operators. And what we end up with, you don't have to look at the details, but we're ending up with a first order rate equation. So we have the change of the Fourier component, so it's no longer a composition a length scale, but a Fourier mode with time equals a rate constant, which is a function of the wave number times the fluctuation itself. And this can be solved by separation of variables and integration, and you end up with a simple exponential function. So we have the change as a function of q as a function of t is the composition at time 0 times an exponential function with t, depending on q. And r of q, standing here, might be positive or negative. So for high q, this will be a negative number. That means that that fluctuation will decay. If it's small, it will rise. And there's also an optimum in that. And that's when you plot R of q versus q, you find your optimum here. And that is exactly that q star. That is the peak that you saw in the first numerical simulation. That's the preferred length scale. So the process is random, but not completely random. It has this preferred length scale programmed into it. And that can be then written down as the square root minus the curvature and the free energy over the stiffness parameter. It doesn't matter so much. And the second parameter that you can write down now is the critical. So above which q do you see a relaxation of the mode, and at what below which q do you see an increase in it. So this is essentially No, this has been done some time ago. You can find this in textbooks. Now we're going to the case of evaporation. So with evaporation, we have to make some clever assumptions, because the previous case essentially counts for a binary blend. There's no evaporation, no solvent. Now we have this ternary blend from which the solvent evaporates. Essentially, if you have a ternary blend and it is incompressible, so the sum of your volume fractions is 1, that means you have two independent volume fractions. You have two coupled differential equations to solve the problem. And that's what we want to get rid of here. We want to simplify it further. So we're saying we're going to redefine our order parameter. We're going to say the solvent partitioning tilt in this tie line at early stages is not important yet. So we get a decomposition between polymer A and polymer B. And at the same time, we have a constant evaporation rate that increases our total polymer concentration, phi A plus phi B, linearly in time. So we have redefined the order parameter, which is the fraction of A relative to total polymer. So there's no solvent in here. And we do the same trick. We express it as a function of time and position relative to a mean value with a small perturbation on top, and we have this constant evaporation rate. That we stick in our Flory-Huggins equation. We modify it slightly, doesn't matter. We do our Fourier transform. And now what happens is that we end up with the same rate equation for Q of t of the initial one times this exponential function. But now R is not only a function of Q anymore, but also of time. So it's no longer a rate constant. It's a time-dependent rate constant. And I've written it out here. You can do the same trick, maximize it, and now you find that the maximum Q, the Q star, also becomes a function of time. And that is describing this increase. And when you look at this equation more closely, you can see that at small times, it will always decay for large Q, but it becomes at larger times this becomes positive for larger Q, and larger Q means that the peak is shifting in time. That's what we saw in the simulation. Now we've done this exercise for a polymer B and a polymer A in a solvent, and for a polymer in a solvent, and you can have exactly the same. You can have a polymer rich and a polymer poor phase. And also there we saw this increase due to evaporation. The math was slightly different, so it looks different at a higher times, but that's where the theory breaks down anyway, because the fluctuations are way too big for the linearization to be valid. So it's about this early stage that we can describe analytically now. The second thing to understand is, what do we then get? So it increases, but what do we get as our initial structure? What is the dominant length scale there? Now, well, there we need to go back to this equation here and stick our tau L into the equation for T, and for R we stick in this one with tau L here, and we end up with this. And now we see what is important to the take-home message here is that instead of a simple exponent time function, we have an exponent time to some exponent. So it's an exponential of time to the power something. And in the limit of slow evaporation, so if this term is much smaller than that one, it is actually exponent time to the power 3. So nothing happens, and then it suddenly shoots up. And the fact that it shoots up means that we actually can talk about a critical lag time, that there is, because the transition is so sharp. And that also, in effect, comes with an advantage that we do not actually need to know the size of the fluctuation of time is 0. And that allows us to extract that from the numerical simulation as a fitting parameter and write the lag time as a function of the other physical parameters in the system. And from that, by plugging that back into this one, we can calculate our dominant length scale as a function of all parameters in the system, basically. So we did a lot of numerical simulations where we change molecular size, molecular interaction, diffusivity, interfacial tension, etc., and we find that at slow evaporation all these curves collapse. So the lines are the analytical theory, and The points are the numerical simulations. And, we have derived based on that the scaling relation for the emerging length scale based on interfacial tension, composition, monomeric interaction, diffusivity, and evaporation rate. Yeah, so that's something that's now that we added to the existing theory of liquid phase demixing. So what happens when you have an evaporating solvent there at the early stages. I want to address the late stages here. That is also changing a little bit, but we didn't see universal scaling here. So here we could really derive a universal scaling relation.
So for that case, you have to use single solvent, right?
Yeah.
So what happens if you have mixed solvent, especially the one that they have very different evaporation rates?
Yeah. That's a good question, because then the pathway through your phase diagrams, what we're working on at the moment, is no longer straight. You can have a kink. Yeah, but it changes things. Yeah, we have not developed any analytical theory for that. But yeah, this is a very interesting puzzle. Mm-hmm. Yeah, yeah.
I know you're just showing a slice of the three-dimensional bulk, or are you just modeling in two dimensions?
I'm just modeling in 2 dimensions or 2.5D. That means that you have a top view and you look down on basically on cylinders, and it depends a bit on how your time scale of material transport relates to your time scale of evaporation, whether that's allowed. Because if evaporation is very fast, you get enrichment of material in the top layer, and if diffusion cannot counteract for that, then you get a layered structure, which might break up. Will be a paper recently coming out on that. But,
a simpler question: how do you model for the loss of mass in terms of the solvent when you just have a two-dimensional system?
We model for the loss in volume fraction, not in mass. Yeah, exactly. When you end up with only polymer. If you only have polymer and solvent, what we see is you extract the solvent, you walk into your miscibility gap, and you walk out of it again. That means you get a structure and it redissolves again until all solvent is gone. You only have polymer left. Yeah. I have a couple more slides on the other topic, which is related because of these droplet-like structure. It's about these OLEDs and why we blend in this insulator. Well, at Paul Blom's group back in Groningen, a lot of work has been done on doing single carrier transport measurements through various organic semiconductors, polymeric semiconductors. And what they saw is that there seems to be this trap level for electrons situated in the band gap, and that is the reason why if you do such a transport measurement, you find that the Hall current is usually a couple of orders of magnitude higher than the electron current. So the idea is that electrons are injected, they can recombine with holes to give light, Langevin recombination, or they can be trapped and wait for the hole to pass by and recombine. This is trap-assisted recombination or Shockley-Reed-Hall recombination, and that is a loss process. There's another loss process is because the electrons are slow, so they make sure that the recombination is actually taking part close to the cathode. So that also means that you have cathode quenching. You want your recombination zone ideally a bit further away. So these traps are obviously an issue. In the space chart limited regime, already in 1962, an equation was derived for the trap limited current. So if you have a current going through a system where you have a trap level that is distributed in energy according to an exponential function, you get this equation. So here's J is the current density. It goes linear with the density of charge accommodation sites in the material, and it goes reciprocally with the trap density in the material to a certain exponent. And this exponent tells you something about the width of the exponential distribution of your trap sites. And for A lot of these polymers, this R is of the order 4 to 5. All the other parameters are constant. Let's say here voltage, layer thickness, we've got dielectric constant, etc., etc. There's an electromobility here. But what is important are these numbers indicated in red, because this means something counterintuitive. If you manage to dilute or decrease these densities by the same factor, you're spacing your sites further apart, then the current will suffer less from spacing your charge accommodation sites than it will from spacing your trap sites apart, because this goes to a power R. So as long as it's trap limited, you will gain in current. If your current is not trap limited, this is not going to help you, of course. So that means that theoretically, if R is 4, then if you have a 10 times dilution, it should theoretically give you a 1,000 factor increase in the current. Right, so what does that mean? Spacing sites apart? Well, because these are organic molecules, you can dilute them. You can blend them with something to make sure that your accommodation sites are spaced. This is simple scheme that I've drawn of the HOMO and LUMO, and here the trap level. And this is an early example from 1996. I think it was PPV, MEH PPV, where we have a Hall current and we have an electron current that is much lower than the Hall current. So that's the situation without blending. Okay, so we've, to begin with, chosen 2 different host molecules with a large band gap. One of them is this PVK and one of them is polystyrene. They shouldn't contribute electronically, they're just there to dilute the semiconductor, which in this case is MEH PPV, but we've shown the effect for various for PPVs, but also for polyfluorines now, so it's actually quite general. And we prepared blends of these polymers with ratios. Well, this is the pure material, and we added more and more of the host up to a 1 to 9 blend. If you go further, then it breaks down because you're going to lose percolation and all that sort of thing. So it's not like sort of an infinite effect, of course. Now, if you do it with PVK, then it seems to work. So this is current density versus voltage. This is the whole current, orders of magnitudes higher than the electron current. And then you start adding the PVK. So here there's only 50% of MEH, PPV 25 and 10%. And you see that the electron current comes up and in the end nearly coincides with the whole current. And this also gives us a factor 2 increase in the efficiency of the device. So it's in line with the prediction according to the formula of Helfrich. We published this earlier this year in Nature Materials. Now if we do the same with this polystyrene, and here all these curves are actually plotted in the same graph, so it's a bit different, but it's essentially the measurements the same. So we have current density versus voltage. We have here these whole currents, and here we have the electron current. So this is the pristine material, 1 to 1 blend, but that a 1 to 3 and a 1 to 9, it decreases again. So it doesn't seem to work. There's no upgoing trend here. And we were wondering what is then different with polystyrene. So what you typically then do is look at morphology. And we see that both of these blends are actually macrophase separated. You have these droplet-like structures. These are 2 different techniques. So this is confocal laser scanning microscopy, where you see in green the PPV-rich phase, and here are the PVK islands or droplets dispersed in it. If you do take this blend, then the morphology is a bit more co-continuous, as it's called. So it's a bit less drop-like, but it is phase separated on similar, roughly similar length scales. So they both macrophase separate. So we figured that is then apparently not a discriminator. So in these solar cells, if you have your droplets, you know it's drawable. You know, you need to do better. You need to make smaller domains. But here we have, in both cases, we have macrophase phase separation. But here, this trap dilution works, and here it does not. I'm not saying that we can explain it, but we have an idea, a hypothesis that I want to present. So we went back to this Flory-Huggins equation with which you can calculate phase diagram. And here's the situation for the PVK. So these are the input parameters that go in. This is the result. So we have here the binodal line, the spinodal, and a fairly large single phase region. And with polystyrene, the theory might exaggerate the size of the miscibility gap. It is massive. It shows that the miscibility between polystyrene and MEH PPV is much smaller. Because here, if you evaporate, you go into your miscibility gap and you get your binodal phases, you see that they're, for a large part of the phase diagram, they are away from the compositional axis. That means that the PVK-rich phases contain some MEH PPV, and the MEH-rich phase contains some PVK. So that means you have macrophase separation, but within your phases, they are still mixed. Whereas with polystyrene, the branches of the binodal coincide with the compositional axis, meaning that if it phase separates, you get pure polystyrene and pure MEH PPV. So there's no intimate segmental mixing within these phases. And that's why we think that it works here and it doesn't work here. We sort of said, okay, if that is the case, then what can we do? We can make sure that we bring this down. So what we can do is we can decrease the molecular weight of the polystyrene. The system gets more entropy. Mixing becomes more favorable. So we took a different molecular weight. In this case, 15N, so it corresponds to 1 kilodalton instead of 40 kilodalton. It's also a very, very silly thing in a way to try to mix two polymers, because usually by a rule of thumb, they are not very miscible. So if you calculate the phase diagram for the smaller polystyrene, then there is this cute little miscibility gap. I don't know if this is even significant. I mean, the model is semi-quantitative only, but it shows that for any of these, it suggests that for any of these ratios, effectively you should get a single phase. And indeed, if you compare the 35K and the 1K, you see that the system is much more homogeneous. To what extent it still microphase separates, we don't know, but there's no macrophase separation going on at least. And now if we do the measurement, we see that the effect is restored. So with small polystyrene, oligostyrene, we do manage to get our increase in efficiency back. So in this case, it suggests that not necessarily the fact that you get macrophase separation is determining, but more the phase composition. What do you get in terms of your ratio of your polymers within your phases is more important. Okay, so that brings me to the conclusions. Well, I hope that I've convinced you of the fact that solvent evaporation really drastically affects the mechanism of spinodal decomposition. Of course, what we did, we used numerical simulations as experiments, and we're still looking for ways to numerically verify it. You have to do scattering techniques. You have to do some sort of scattering. But it needs to be sensitive enough that it picks up the compositional contrast in these early stages. And I can imagine that that can be quite challenging. There seems to be a universal dependence of the emerging fluid structure on evaporation rate. And for the other topic, it's interesting to see that, or that's how we interpret our results, let's say, is that phase composition can, under certain circumstances, be more important than the mere fact of macrophase separation or not, like in this trap dilution experiment. Then I'd like to thank these people, especially my recently graduated theory student, Charlie Schaefer, for doing all the hard work in deriving the linearized model. Great guy, great mathematical creativity. And of course, you for your kind attention. Thanks very much.
Questions?
So from your model, if you have just one polymer and a solvent, and then like if I say I want to test it in a smoother surface, so is it like low boiling point solvent or high boiling point solvent would have?
That's a good question. So boiling point, so it depends whether different modes of phase separation can compete. So, for instance, with the solar cell blend, we know that if we take a higher boiling point solvent, that you can, for instance, crystallize out or your polymer or your fullerene before you hit the miscibility gap. So we need chloroform there to really quench the system into the miscibility gap before anything else can happen to have these droplets, so to say. But there are, if you take two amorphous polymers in a solvent, you have all the time of the world to make them phase separate. Let's say you can make them. You can take a much slower evaporating solvent and still you gradually walk into your miscibility gap and you get your demixing. So I don't know if that was your question exactly, but.
I think the question was like if you have to take a single polymer and solve
A single polymer.
Yeah, I think
A single polymer, yeah.
the final equation where they show that if that term high boiling point or low boiling point, it would go into that evaporation rate
Yeah.
parameter.
Oh yeah, yeah, sure. Yeah, yeah, absolutely. Yeah. 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 Okay, I would say I would then go for maybe a higher one, because with a single polymer in a solvent, if you have phase separation, then you get, for instance, you get polymer-rich droplets in a polymer-poor environment. You want that situation to relax again. You want these droplets to redissolve again at the end of your film formation process to get a smooth film, right? So you don't want your polymer droplets to dry, cross a glass transition, and end up sort of semi-coagulated on your surface, because then you have a dynamically trapped situation, and then you would need to give the system time to redissolve again, intuitively. That's what I would say for a polymer solvent system. Yeah. Yeah.
Or before it. That's good, because I need to like organize the question in my head anyways. Okay, so the way I understood the second part of your talk is that at first you have this too good of a phase separation between polystyrene and the PPV, right? And at this point you don't feel the effect of dilution on the diluting the traps.
Right. Okay.
So that suggests that there's some kind of critical phase separation, or miscibility rather, between them. But they need to be small enough for you to feel that. And I'm wondering if you have any idea of how intimately mixed do they need to be?
That's a very, very good question. Yeah. I mean, this is actually such a big question for us at the moment that this is the next project. I mean, how intimate can? So we're working on this. It's I really can't answer it. We did this. We took this AFM image. We can't see any big structures, but and we're very interested in how this relates to the electronics. You know, so yeah, because I mean, there's all sorts of things going on. Of course, a polymer, if you start diluting it, then I can also imagine you have more intra-chain transport than inter-chain transport at some point. It's not anymore a homogeneous situation of charge accommodation sites dispersed in the medium. So it also will become anisotropic to some extent, I think. So, but yeah, these are all questions to us. Yeah.
So another question, I know that we in the community really curious. So what exactly are traps in this particular system? That's why when you dilute it out, but you also need mixing, and then you see it work better, right? So what exactly are electron traps? I know in the other paper a couple years ago, they suggested that, some sort of water oxygen mixture. But if that's the case, you mixed it in, perhaps, that may not be the dominant roles.
Well, of course, this Helfrich theory is purely physical, right? It says irrespective of what it is, this is what you should get if you space your trap sites apart and space your accommodation sites apart. It's a good question. It's not precisely known what traps are. Are they chemical in nature or physical or both? Is it simply some sort of redox reaction? So is a permanent trap the formation of an OH minus or not? Are they kinks in the poly? These are all questions to us. So this, I mean, this is not answering what a trap is.
Yeah.
Absolutely.
I'm just curious just to see why dilution that help.
Yeah.
So I have another question regarding, so you do the phase separation in this direction, right? I mean in the lateral direction.
Yeah.
The reason I'm asking that question because that related to the work done by Michael. So when he also mixed conducting polymer with the polystyrene, and he also reduced to very small amount of conducting polymer, like 1 to 9, the ratio.
Okay.
But for that particular case, we think that they are vertical phase separation.
Yeah.
So somehow the conducting polymer go down to the bottom.
Yeah.
And then so because and then you do transistor transport, it's still very efficient.
Is that transistor transfer?
No, that's the diode,
No,
right?
that's
Diode.
yeah.
Yeah, so I'm just curious that if you have thought
Yeah.
about that or know a bit about that.
Yeah. So that's quite a complex question. There's a couple of things going on. Look, the spinodal decomposition is material flowing from low to high concentration, right? You cannot model that with Fickian diffusion. Yeah, no, I'll come to that. But outside it is materials always flowing from high to low concentration. It means somewhere in the middle there's a zero mobility, and that's exactly on the spinodal. So that means that the dynamics of your system will depend on your ratio, how close you are to the spinodal. And if you see stratification, so if you need to get a sort of one film on top of the other, this is usually a stage where it goes through either very quickly or not. But depending on the dynamics, you're freezing in this stacked system, or it forms very briefly and then breaks up in these small droplets and forms lateral islands. I've done some work on this together with Alan Moons, which also says hello, by the way. So that's one thing. That's the dynamical side. So that can depend on your polymer-polymer ratio. Another thing is, of course, preferred interaction with the substrate, right? So one polymer may be attracted by the substrate preferentially. Another thing is evaporation itself. If one polymer is slower than the other because it's slightly smaller slightly bigger, then due to evaporation, the fastest component, which is usually the smaller one, will be moving away from the air interface quicker. It will counteract the concentration gradient quicker, and that will, without any specific surface interactions, already lead to stratification. We hope to publish on this soon. So there are all sorts of effects that can be going on that give you stratification.
I have one question. Can you go to the data where you show the low molecular weight polystyrene blend and the impact on the current? Okay, so we got 90% polystyrene. We got a higher current, and presumably it's mixed, well mixed. So, this is something that we struggle with. So you have there, 3 order of magnitude increase in current at 10% of the volume of the semiconductor. So your conductive paths have to be a lot more efficient in a situation where the electronic coupling between the conjugated polymers, if it's miscible as, if it's fully miscible, then I don't know how it's going to get from one to the next, right? So somehow maybe, even though it's miscible, there's got to be some contact between the chains.
Right.
And then the other thing, it implies that the current transport through those contacts has to be exceptionally high relative to the initial condition, right? Because
Okay.
you're at 10% and you're already 10% that's diluted.
Mm-hmm.
So how do you envision the difference in the transport channels for the carriers
Mm-hmm.
on the bottom condition relative to the blue condition? That's the difficult thing to, one thing is to
Yeah.
consider the trap density, but then when you think about the transport channel, then it gets hard to
Yeah.
accommodate. And if, anyway, so that,
Yeah. So that's obviously also a question that we have. We also went beyond this point. So make a 1 to 20 blend, or so to push it further, and then you see that it breaks down at some point. So.
you think that's the percolation breakdown?
Yeah, we're still above percolation limit here. Paul had some literature from the past that showed that 10% is still, in terms of percolation, I'm not talking about conformation or which could be related to that. One thing you could look at is the hole current. So the electron current is trap limited, and due to this dilution, you have less problems with the traps. But the hole current here is somewhat lower than in the pristine material. I don't know why it coincides with the others. You would maybe expect it to come down further because you have less material present, but it does not. We have been thinking in terms of conformational changes on the chain level, the polymer chain level. And that's why at the moment we're also trying to do solid state NMR experiments to see if we can pinpoint any changes in the conformation.
The tricky thing there is because if you're on diode, your chains are not really aligned this well, I don't think. So if
They have no reason to be.
If you're changing the conformation, maybe the lateral transport is going to be much more affected than the vertical transport. So the question
Maybe that's a very nice idea, actually, to measure the current anisotropically.
right.
Very nice. Yeah. Mm-hmm.
Another question I have is, have they looked at the activation energy as a function of dilution, just to see whether it change at all? Because
Yeah.
this come back to the point you were mentioned earlier. Maybe in the wall film, you have basically interchain and interchain transfer.
Right. Yes.
But when as you dilute, now you force it to go more like most of the time through the interchain transport. If that's okay, you may be able to see a bit different in the activation energy as a function of that.
Right. They have looked at that definitely. It's in the Nature Materials paper for PVK. And I don't recall, I'm sorry, the results exactly, but
I remember I saw
yeah,
the
the
talk, but I
temperature.
don't remember seeing
Yeah. Okay, good. Sorry for that.
I am going to be very rude and I will terminate this discussion due to time limitations. And I'm sure that we can continue the discussion later. Let's all thank Jasper once again for a great presentation.
And thank you, Winkman, for inviting me. I should have started with saying that, but yeah. But it's a good question.
I wondered, if it...
I can make it even worse for you with PVK. Do I have